Welcome to another open learning session where I'm going to catch up with deep learning. So I'm currently working on the mathematics for machine learning, the book. If you have followed one of the other videos, you would see that today's chapter is matrices. So let's just start. Matrices play a central role in linear algebra. They can be used to compactly represent systems of linear equations. But they also represent linear functions, as we will see later in section 2.7. Before we discuss some of the interesting topics, let us first define what a matrix is and what kind of operations we can do with matrices. We will see more properties of matrices in chapter 4. So, okay, first the definition. Definition 2.1, matrix. With m and m element of the set of natural numbers, a real-valued mn matrix A is a n times n tuple of elements, aij, with I from 1 to n and j from 1 to n, which is ordered according to a rectangular scheme consisting of m rows and n columns. Okay, so let's just use plain language here. A matrix is a box of numbers. And the numbers are organized in this schema where we have number of columns is n and the number of rows is m. Now it's important to understand that the order in which and how we are writing this down is important. What we are having here is m times n. First, the number of rows. So how deep is it? And then the number of columns. This is what we have to remember. By convention, 1n matrices are called rows and m1 matrices are called columns. These special matrices are also called row-column vectors. Okay, so a vector is basically a special version of a matrix. So let's try the first version. So we said first how deep it is. 1, basically one row. Okay, so it would be something like A1, A2, A3, AN. And okay, this would be that. And then we have the other case where M is basically how deep it is. So, and it has only one column. So A1, A2, AM. Yeah, that makes sense. Rmxn is the set of all real-valued mn matrices with a element of that set can be equivalent represented as a, small a, element of Rmn by stacking all n columns of the matrix into a long vector. See figure 2.4. 2.4? I'm not sure this is 2.4. Here on the left side. This is figure 2.4. And what are they saying? They say by stacking its columns, a matrix A can be represented as a long vector. Okay, that's important. So instead of having like a matrix like a classical one, where you have some kind of a box, you just say, okay, we reshape it. I remember in PyTorch, or in NumPy, it's a Python library. You have like these reshaping operations, and then you get completely confused. Sometimes it works, sometimes you have to reshape it, and then it works. So what they're saying is everything is basically a vector, like an array. So we have a matrix 4 deep and 2 wide, and 4 times 2 is equals to 8. So this is the same as just having an array which is 8 deep. And I think this is important for machine learning because memory is the memory is always a stack of things. It's one-dimensional. You have an address and then you have some kind of space where you can put things in. And it's one-dimensional. It's basically a really, really long array. And if you want to do matrix operations, then you actually, like on a physical level, you do it on this array, on this long vector. Even though, like from mathematical point, it's a matrix or something like that. This is something we need to understand for machine learning. This reshaping part. Okay, I'm going to clean up a bit here. So I think what's important is this part, that RMXN. I'm not sure how to say that. It is a set of all matrices. So it's not one set, but it's not one matrix. It's a set of all the matrices which can have the form of MN. And A, capital bold A, is a matrix. And each matrix can be represented as a vector. This small bold A is a vector, this one. And what they mean here is n times n. So this is a single number. For example, here we have 8. So we take this definition, and then we can say we can also represent that as a long vector. Okay, so do we need to remember the definition, or is it obvious? Let me think. Like, I'm mostly doing this just for myself. At the end of each big chapter, I will write some kind of a summary. So I need to know what actually is important. Things I already completely understand, I don't write it down. But please feel free to have you take your own notes. I think what's more important here, like this one is obvious for me. I would not write this down, but the ordering of things are important. Yeah, so I just made it here as a little box. It's important that it's first it goes down, then it goes wide. It goes deep, then it goes wide. I don't know, maybe some people say height. For me it's more depth. Maybe I'm wrong. I guess I'm wrong. I think most people would say height. But does not really matter. How many layers of rows can you stack? That's the first thing you want to ask, or you want to read from this M and N. And then how many columns do you have? Maybe rows over columns? I don't know. Okay, so let's go on. Next one, matrix addition and multiplication. The sum of two matrices A and B, in this case they both have the same dimension, is defined as element-wise sum. So you have A and B, then you say, okay, top left both plus, and then here top right, and basically you put each other on top of each other. Like you put the second matrix on top of the first one, and then you punch the holes. That's how I would think of matrix addition. Yeah, I think this is something I can write down in the notes. And then we have matrix multiplication. C is equal to AB. And the important part is here that, as you can see, we have here different dimensions here. We start with the first one, m times n, and then we multiply that with n times k. And the trick is that these one, they need to connect. It's like, I don't know, like chemistry or something. Like they have to like connect. They have to be the same thing. Maybe Lego bricks. And then you form like a new, I don't know, like a new brick. And this is basically m times k. So, and the interesting part is if you reverse those two, then it would not work, because then you would have something like k times n times k times m times n, and k and m are not working together. They are not the same. Okay, and how does it work? How you do the actual multiplication here? What they say is you basically loop over the n thing. It's in both cases the same. And then you have a new matrix, and the first element of that new matrix, we know that first you go down. So let's just take blue for the first matrix. First you go down, and then you go to the side. And because we are looping over the second one here, we will go only from left to right in the first matrix. And the second matrix, the first one is down again, and the second one is to the right. And here you go down. This is basically what you need to know for matrix multiplication. It makes sense because once you know that the matrix multiplication you have to connect, then they can only connect if they have the same number. So let's say the number is n is 3. Yeah, we have 3 and 3. Then you know that the first matrix is 3 wide and the second is 3 deep. And here you know that we loop over n. In this case, they use just L as the variable. So first you go, let's use the right colors. So first you take the first box, then you take the second box, then you take the third box, and then you go to the next one. And in the second matrix, you take the first box here. The second box is, but it goes down and not to the right. And this is how you do the multiplication. So this one goes with that one goes with that one goes with that one. And what you do is you do a multiplication. Okay, so let's try to write this down a little bit cleaner. Let's do a 3 times 2 and a 2 times 3 matrix. We know that, let's just use variables. First it goes down and then it goes wide. So A, B, C, D, E, F. This is our first matrix. Then we go down again. G, H, J, no, first I, right? I, H. So we know that our n is in this time 2. So we want to know what is C11. And we know basically we have C11, we have C21, we have C31, we have C21, C22, C23, C31, C32, so C33. So that's so this one is calculated by looping over basically over a set of 2, because n is a 2. So we have to do now here this part. A1L. Sorry, L is not. L is 1 and I is 1. So we take this one and then we take this one because J is 1 too. And then we do the same thing for 2. So we take this one and then we take that one. I think it's better to put it in different colors. C11 would be equal to A times G plus D times H. And then you do all the other elements as well for C. Yeah, so you might think of, this is quite complicated. Is there an easier way to understand this? Let's try to find an easier way to understand this. First of all, you have something like, I don't know, like a stripe. Then you do the overlay. So let's try to imagine these two. So you have these two stripes. The first one, the green one, goes from left to right, and the other one goes from top to down. But they're the same length, if you want. Yeah. So they have the same length. Ah, that's why they put an L here, I think. Here. But the important part is they have the same length. So what you can do is you can do this part and this part, and that part and that part. So this would be the first part, the C11. And now if we are moving to C21, what would change? Okay, so one thing what would change is that the green one would change one down, but the yellow one would not. And this is basically a new combination, right? And then if you go to the third C, the C31, you would move that down. But the yellow stripe would not change. And this is another new combination. And if you go back to the second row, the first one, you will go back here, but you will change that one. And then you can go over that again, right? You can go here another one for C22 and then C32. And then C31, what would that be? So C31A is, or A would start here, right? No, wait. Okay, let's do it again. C11 means that A is A11 times B11 plus A12 plus B21. Yeah, exactly that. And then if we want to go to C21, we start with the 2 instead of the 1. So the green one would be that one. And if we start with a 3, oh, I see. The error is my writing here and here. Well, that's not good. That makes everything more complicated. So it should be like this, right? You start with the depth, the height, because this one is the last. This one is the last row. It has to be 3 in the beginning, and here we always have a 1 in the beginning, and then 2 and 3. Yes, this is much better. This makes much more sense. There's another problem here. Yeah, unbelievable how many mistakes you can make. But I guess this is actual learning. Okay, so let's start again with C11. C11 goes like this, where we start with 1, 1, like the first. Okay, this is C11. C12 means that green still is in the first level, but yellow goes one to the right. Or is it right? Yeah, so obviously, I'm not sure how I could not see that. We have a wrong matrix. K and L are missing. So now we have a 3 times 2 and a 2 times 3 matrix. Okay. Okay, that was quite annoying. But yeah, that makes sense. That makes sense. So now we can say that C11 is exactly this one. And now if we move to the right to C12, we just move the yellow box. And then C13 goes one more box. And then if we change the row, we just change the green one. And then we go again, the yellow one to C22, now to C23. And then to go back to C31, we do this. We reset the yellow box and we just move the green one down. And then we move that to C32, and for C33, we just move to the last one. Yes, so every time we have a different combination. That makes sense, because every value should be different, right? But at least it should be computed with some kind of different elements. Just reading this is not enough. Like, understanding it is much more important. How can we write this down to make sense of it? Okay, I guess this is like a prime example for doing exercises. Okay, so I guess learning the definition is important for both, and then doing exercises. I'm not sure how you can write this down to make sense of it. Okay, so I guess this is just the same as we figured out. Let's read it. This means to compute element Cij, we multiply the elements of the ith row of A with the jth column of B. Yes, exactly. And sum them up. Later in section 3.2, we will call this the dot product of the corresponding row and columns. Each one of those C's is a dot product, because we are basically multiplying two different vectors. Yellow is a vector, and this one is a vector, and this one is a vector. And each time we move that, we're moving, basically, we can construct 9 different dot products from these two matrices. Okay, we call them dot product. In cases where we need to be explicit that we are performing multiplication, we use the notion dot, A dot B, to denote multiplication. Remark, matrices can only be multiplied if their neighboring dimensions match. For instance, n times k matrix can be multiplied with a k times n matrix, but only from the left side. Okay, the left side thing means that you cannot reverse it. You cannot do like A times B is not the same as B times A. That's what they are saying. The product B, A is not defined if M is not the same as B, as N, since the neighboring dimensions do not match. Remark, matrix multiplication is not defined as an element-wise operation on matrix elements. So it's not just that we take the elements, like in the case of an addition, and just multiply them, like we punch the holes, if you want so. It's not. Even if the sizes of A and B was chosen appropriately, so if they chose the same. This kind of element-wise multiplication often appears in programming languages when we multiply multi-dimensional arrays with each other and call that a Hadamard product. Okay, so there is a different kind of multiplication called the Hadamard product. And that is basically, we use the same logic when we're doing the addition, just we don't do the addition here with plus, and then with plus, but we do the multiplication. Example 2.3. A is this, B is that, or exactly the same as what we have seen, and well, no, it's the reverse. It's 2 times 3, not 3 times 2. And then we do the addition, the multiplication. B and A and B is something else than B and A. Oh yeah, that's interesting. We can do both. We can like do the AB and the BA. That makes sense. Yeah, so maybe I will just do the multiplication here by hand. All right, so here I just copied into the board. I'm just doing the multiplication again. Okay, so we want to do A times B. So the first thing goes from left to right. Let's do the, and the second one goes from top down. Okay, let's do the multiplication now. What we are doing is we do A and B. That means that it should be a 2 times 2 matrix in the end. I will give myself some space. We will have 1 times 0 plus 3 times 2. And then we move on the green one to the left. 2 times 0 plus 2 times 2. No, that's not right. That's not right. Okay, let's just, without looking, we need to think. I know that they have to reverse the boxes. I know that I have to reverse the boxes. And the reason is because in this case, the connected dimension is 3, and here 2. The box has to be 3 dimensions, or 3 long if you want so. And we go from, we know that the first number in the dimension is the height, and the second one is the length. So because it's the second one, the 3, this one has to go like that. So the green box has to be this one. And here the yellow box is the first number, which is the height. So we have to do this. So, okay, this is how you actually do it. And then you do the calculation together. Maybe now I can just do the number in my head. 0, 1, 0 is easy. So this one is 2. Then you go green 1 down. It would be now, so green goes 1 down. If green goes 1 down, I would assume that if green goes 1 down, we are actually doing the number here. That would make more sense. Let's do it like that. This would be 2 as well. And then yellow goes 1 down, 1 to the right. Then we have 2 minus 2, that's 3. And then the last part is 6, 4, 5. Okay, let's do the second calculation. We know that the second one is, we should have a 3 times 3 matrix. Okay, again, we have B times A, which means we should have a 3 times 2 matrix. What disappears is the 2. And in this case, it should be this one. And on the other side, this 2 disappears, which is this one. So let's do the multiplication. We have 6. Now I'm going to move to the right. So I will move the yellow box in my head. So this one would be 4. And the last one would be 6. Now we can move the green box 1 down in our head. Then it would be 1 minus 3, so 2. and then we move the yellow box, which is 0, and then again the yellow box, then we have 3 minus 1, it's 2. Then we reset, the green one goes down, down, so 0, 1. Then we have 3, 2, 1. I guess, I hope that was right. Okay, let's just check the... Okay, let me check. Yeah, so the first A, B is correct, and the second one is not correct. The last one is correct, the last row. The first row is somehow, the last is not complete. Maybe I made errors with doing it in my head. Oh man, am I that bad in doing math in my head? Okay, so let's do it again. So it was 1 times 0 plus 3 times 2 is 6. Okay, that's correct. Then we have 2 times 0 is 0, and then the next one is 4. That's correct. The last time is 6. 3 times 0 plus 1 times 2 is 2. So this one is 2. Okay, second row. Second row is, we moved the green one down. So it's 1 plus minus 3, which is minus 2. Yes. 1 plus minus, sorry, not 1. We are moving both down. Wait, what am I doing? To calculate this one, we have to move here and that one here. Yes, that's correct. So it should be 2 minus 2. It's 0. That's right. And the last one is 3 plus minus 1 should be 2. That's correct as well. Okay, last row. Last row is completely wrong, right? No, it's right. Yeah, so I made some mistakes in my head, but basically the algorithm was right. Whew, all right, good. Let's move back to the textbook. Now, okay, from this example, we can already see that matrix multiplication is not commutative. AB is not equal BA. See also figure 2.5 for an illustration. Yes, exactly. That's what we already know. Definition 2.2, identity matrix. So we define the identity matrix for n times n as basically zeros except what we have in the middle for each row and column. Okay, so the important part is that I think the identity matrix is only defined for square matrices. So it contains a 1 on the diagonal and 0 everywhere else. Now that we defined matrix multiplication, matrix addition, and the identity matrix, we let us have a look at some properties of matrices. Associativity. For all matrices in M times N, and given that there is a matrix B with N times P and C P times Q, we can say that if we multiply A times B first and then we multiply it with C, it's the same as if we multiply BC first and then with A. What they're saying is you can break down matrices. I would not say the order is not important because B and A is not A and B, but the order in which you do the matrix multiplication is not important. I don't know if that makes sense what I'm saying. Like, at least for me, it makes sense. So, like, the overall order is already defined. A times B times C. So it does not matter if you do this part first or if you do that part first. But that A and then times B and then times C, like the overall direction, has to be the same. But you can like group these matrices, these multiplications first, and it has no effect. I think this is quite important to at least to understand or to have the right vocabulary. Associativity. And then we have the second one, distributivity. It says that we have another matrix A, B, and matrices A, B, C, and D. What they say is you can group out the matrix. It's like with like even when you have different terms and just doing simple math, you can group out C. So you can do the addition first and then you can multiply with C. And I think these are important for doing optimizations. Like if it's possible to group a bunch of matrices together and then add them and then do the multiplication once, it's much more efficient than like doing the multiplication twice and then add them. Because you can think of here we're doing one multiplication and one addition, one multiplication, and here we are doing one multiplication, one addition, and one multiplication. So 3 operations in total, and here we have 2 operations in total. Okay, so there's another point, multiplication with the identity matrix. So if you multiply with the identity matrix, it does not change. You just have to make sure that the dimensions match. So the identity matrix M has to be on the left side and the identity matrix N has to be on the right side. But still does not change the matrix A, which makes sense. Okay, these 3 are quite important. All right, so I think here I will do a short break, or maybe a long break, I don't know. What is left is inverse. Oh, okay. It's just that. All right. See you next time.